Thank you very much. I'm going to begin my talk with a question, and that is, from what perspectives should we view the statistics wars? And I say it should be from the standpoint of the ordinary skeptical consumer of statistics. For her, there's a minimal requirement. If you haven't done anything to rule out flaws in your claim, then we don't have evidence for it. We only have evidence for a claim to the extent it has been subjected to and passes a test that probably would have found it flawed just if it is. This probability can be called the stringency or severity with which the claim has passed the test. This applies to any methods now in use, not just tests, but also estimation, prediction, or just in general solving a problem, even if it's informal. Now, I'm going to focus on the most controversial area these days, and that's statistical significance tests, their battles, and some paradoxes surrounding them. Statistical significance tests are often fingered as the culprit of the replication crisis. They say it's too easy to get small p-values. On the other hand, what is the replication crisis except that it's too hard to get small p-values when others try to replicate with stricter control? R.A. Fisher always said, it's easy to lie with statistics, with selective reporting, this political principle that anything can be proved with statistics. Yes, sufficient finagling and cherry picking, data dredging, and optional stopping may result in a claim appearing supported, even if it's unwarranted. So I'll call these biasing selection effects. This underwrites a key aim of statistical significance tests, which is to bound the probabilities of erroneous interpretations of data. I call these error probabilities. They're really a small part of a general methodology, which I call error statistics, that includes not just tests, but also confidence intervals, resampling, randomization trials, and other things besides. Remember when fraudbusters like Yuri Simonson used significance tests to expose fraud, to show data too good to be true, that you couldn't explicate under sampling variation? How is it that tools relied on to show fraud, questionable research practices, lack of replication are now said to be used to tools we can't trust? It's as if, to some people, p-values can't be trusted unless they're used to show p-values can't be trusted, as the title of one of my blog posts. Now, Simmons et al. Recommend a 21-word solution that the researchers state ahead of time the stopping rules, the hypothesis, all in the introduction to an article. Yet, oddly enough, some of today's reforms are actually at odds with the 21-word solution. So what are significance tests? Starting with simple Fisherian tests, in a paper with David Cox, we said their goal is to test the conformity of the data under analysis with some reference hypothesis, H0 null hypothesis, in some respect. The p-values, the probability the test would have yielded an even larger value of some test statistic under chance variability alone. That's not the same as the probability of data under H0, right? Though some say. The p-value is a counterfactual claim about what the test would do in general. The reasoning is this: small p-values indicate some underlying discrepancy from H0 because very probably 1 minus p, you would have seen a less impressive difference if it were true. So it satisfies this severity requirement. But even if small, it's still not evidence of a genuine statistical effect, call it H1, yet alone a scientific conclusion, H star. Only abuses of tests would commit such a howler. Of course, until an audit, as I call it, until you've checked the underlying assumptions, you should distinguish it. To do so, I call it an indication instead of evidence. Neyman and Pearson put Fisherian tests on firmer ground. It was Egan-Pearson who called Neyman in from Poland to help, because the Fisherian tests seemed to have too much latitude, enabling just the kind of fallacies that we are so on about today. So they introduced the alternative hypothesis to cure this problem. They introduced the trade-off between type 1 errors and type 2 errors, and they restricted the inference to statistical alternatives within a model, so you couldn't jump outside to some substantive scientific claim. Of course, you won't see these called Neyman and Pearson tests. They'll probably be called test of statistical hypothesis, which is fine, or statistical decision-making, which isn't so fine, in my opinion. But Fisher and Neyman engaged in these pathological battles, which really set the whole field into the battle mold for decades. The success of Neyman-Pearson optimal error control led to a whole new paradigm in statistics, which is still very important today, but it overshadowed Fisher's more informal views. Then there was the fact that they were all in the same building at University College London for a while. As David Cox says, it brought them too close to one another. Not to mention that Neyman didn't want to use Fisher's book, and for some reason they wouldn't let Fisher teach statistics. It's kind of crazy. The contemporary casualties really do reflect the old pathological battles. For one thing, we hear that Neyman, Pearson, and Fisher tests are an inconsistent hybrid, where Fisherians can't use the Neyman-Pearson style power, and Neyman-Pearson testers can't report p-values, but only fixed error probabilities. And that is wrong. In fact, Fisher and Neyman-Pearson themselves recommended both pre-data error probabilities and post-data p-values. What really happened concerns something you won't hear about, and that is Fisher's fiducial probability. And just to hear the fallacy in the most familiar terms, Fisher was claiming that a confidence level measures both error control and gives you a post-data error probability on statistical hypothesis, but without prior probabilities, at least in special cases. But it led to inconsistencies, and he would never admit that he'd made a mistake. This is from I.J. Good, one of my colleagues from long ago, who says so many people assumed for so long that the fiducial argument was correct. They lacked the chutzpah to question it. But Neyman did, and he developed confidence intervals to deliberately emphasize the performance rationale to avoid the slippage and the error that Fisher was making. So am I saying we need to know the history of statistics to get beyond the statistics wars? Well, no, somewhat the opposite. I'm saying we shouldn't be hamstrung by battles from 70, 80, or 90 years ago, or to what some of today's discussants think they were about. And that, I suppose, is Egan over there. As I say someplace in my book, it's the methods, stupid. A key question remains, though, from this whole fiducial battle, and that is, how can we have a post-data quantification of epistemic warrant that's not a posterior probability? I say we can do it with severity, and this is closely related to David Cox's idea about calibration. We have to calibrate methods, much as we would do measuring instruments. We've got to know how they would behave in actual or hypothetical repeated uses. He had this principle, the weak repeated sampling, which says that any proposed method of analysis that in repeated application would mostly give misleading answers is fatally flawed. But good performance is not sufficient for a good inference measure. And Cox gave us a famous example, the so-called weighing machine example back in 1958 that shows this. He emphasizes that we need to know that the calibration is relevant, taking account of how the data were obtained. But we don't want to go so far as to get to the unique case, which would preclude error probabilities altogether. However, interestingly enough, rivals to error statistical accounts do condition on the unique case. In their view, all the evidence is via the likelihood ratios, and this would be the probability of the data under a hypothesis. Here, the data are fixed. The hypotheses vary. So, for example, any hypothesis that perfectly fits the data is maximally likely. And you see that it's different from probability because you can have many rival hypotheses, all of which perfectly fit the data. And so they all have maximal likelihood, but clearly couldn't be with probability. And we know that it's easy to get such well-fitting hypotheses with precisely the biasing selection effects that we're on about. So this is the subjective Bayesian, Dennis Lindley, saying, of course, all error probabilities violate the likelihood principle, significance levels, power, because they all depend on something more than the likelihood function, something irrelevant for Bayesian, namely the sample space, by which he means that once the data are in hand, that you don't consider outcomes other than those that already occurred, but error probabilities rely on that. So inference by Bayes' theorem entails the likelihood principle, which entails no error probabilities. Many of today's reforms that were offered as alternatives to significance tests follow the likelihood principle. We hear Bayes factors can be used in the complete absence of a sampling plan. Or it seems strange to some that the frequentists can't analyze data if they don't know the stopping rule. Don't data speak for themselves? Asked Berger and Wolpert in their book, The Likelihood Principle. Well, not to the severe tester and not to the error statistician. Here's a famous example of testing the mean of a normal distribution, two-sided. Suppose you don't get significance after the first n trials and then go on to take another n, still not significant, take another n, etc. The error probability quickly balloons so that the probability of erroneously rejecting the null is much, much higher than the 0.05 or whatever that you thought. It's fascinating that the likelihood principle really parallels the holy grail in my field, in philosophy, parallels the logics of induction and what they were after. And I was brought up on this whole idea that what we need to do is find these confirmation relations between statements of hypothesis and evidence, and everything else doesn't matter. Popper, who was fighting Carnap, Popper was a falsificationist, and he said we're just simply deceiving ourselves if we think we can interpret any of these C functions as degree of corroboration or anything like it. He too wanted severity and he had a notion, but he never fleshed it out adequately. But the fact that he couldn't do it doesn't mean that modern day statistics can't, and I think it can. Okay. Now, Fisher, Neyman-Pearson, they had a philosophy too, but it was pragmatic, and they were allergic to the idea of a single rule for an ideally rational inference. They were key tuned in on how to control human biases, and they did so via planning, experimental design, randomized controlled studies, and so on. But there was a very important link to formal statistics, and that is that the biases would directly alter a method's error probabilities. How to figure this out and how to sustain this is certainly not automatic. It requires a lot of background knowledge. So when you hear that frequentists don't use background knowledge, it's not true, and they may not use priors if they're not frequentists, but they use quite a lot in the form of the design principles. Now, Bayesians can also block inferences based on biasing selection effects with their prior beliefs without error probability. Casualties there, for one thing, it doesn't show what researchers had done wrong. It's the multiplicity. The whole thing becomes a battle of beliefs. And really, there's nothing more seductive than data-dredged hypothesis for seemingly believable claim. Moreover, there's an additional source of flexibility. Now you've got these priors as well as biasing selection effects. And priors can also be data dependent, and it's never clear how to interpret them. Jim Berger had an important peace treaty with his default objective or non-subjective problems. They found that it was rather hard to elicit people's opinions, even if they were expert. And so they developed these accounts that improved on something that Harold Jeffrey had built several years earlier. And the idea is to prevent the prior beliefs from influencing the posteriors. It was to be data dominant in some sense. But casualties, it isn't clear that these default priors are going to be expressions of belief or uncertainty. We know they may not even be probabilities being improper. And there's still no real agreement on rival systems, even though I know Jim Berger is working on this. The reconciliation that it offers leads to violations of the likelihood principle, forfeiting strict Bayesian coherence, and whether that's a casualty or not will depend on your view. But we still don't get full-out error statistics. A key battle in the statistics wars, old and new, is the difference between p-values and posteriors. A p-value can be small, suggesting evidence against the null, but a posterior probability on that null can be not small or even large, suggesting evidence for the null. To a Bayesian, this shows that p-values exaggerate the evidence against. But to others, this is just a reflection of the fact that Bayesians can disagree sharply with each other. This is a quote from Stephen Sen, because there's a great deal of leeway, and many think that this is really a Bayesian family feud as to whether we should even be testing this point hypothesis. And what they do is give a lump of prior probability to the null and then smear the rest along the alternative. And depending how you spike and how you smear and even select the alternative, an alpha significant result can even correspond to a high posterior, even as high as 1 minus alpha, where alpha is small. But a deeper casualty here is assuming that there even ought to be agreement between quantities measuring different things. Okay, my final topic. There are battles between officials, agencies, and journal editors, and many unintended consequences. The American Statistical Association had a task force on statistical significance and replicability, in which they state P-values and significance testing, properly applied, shouldn't be abandoned. The controversy is really all about misunderstandings, lack of appreciation of uncertainty and variability, and so on. So why did we need this blue ribbon panel making up the task force? The reason is they needed to be created to stem the casualties of an ASA director's editorial in 2019, which said declarations of statistical significance should be abandoned. You can use p-values, but don't assess them by preset thresholds, regardless of how small. I call this the no significance, no threshold view. Here are some unintended casualties. It appears from this that statistics is withdrawing tools for a major task to which scientists look to statistics, namely to distinguish genuine effects from noise. It's like after all these years, they're saying, never mind. And even to suppose that this is ASA policy, which it isn't and never was. The most serious casualty, as I see it, is that researchers lost little time of saying, well, if we're going to abandon significance tests, I guess we don't need type 1 error probabilities anymore, right? Given the discussions to abandon significance testing, it may be useful to move away from controlling type 1 errors. And these are researchers in radiation oncology. Well, the question is, useful for whom? Not for our skeptical consumer of statistics, for her to evaluate a researcher's claim that this is a benefit for her, this radiation treatment. She really wants to know how many chances did the researchers give themselves to find a benefit, even if spurious. It's not enough that their informative priors, as they tell us, favor the intervention along the lines of trust us, we're Bayesian. Moreover, if you can't say about any results ahead of time that they won't be allowed to count in favor of a claim, that is, if you deny any threshold, then you don't have a test of that claim. Is anybody here suggesting that we use methods with error probabilities over 50%, thereby violating Cox's weak repeated sampling principle? I don't think so. Neyman-Pearson had an undecidable region, which I think is right. But even there, we can distinguish quite horribly supported claims from rather well-tested ones. Some say, you know, we don't worry about type 1 error control because we already know that all null hypotheses are false. This claim really boils down to saying all models are strictly idealizations, but that doesn't mean that you know all effects are real. And if you really do get rid of the sampling distribution, it's not just type 1 errors that go. All error probabilities, type 2 magnitude, they all depend on the sampling distribution. Now, I've long argued against some of the howlers and abuses of statistical significance tests and other methods, and I propose to reformulate those methods in terms of discrepancies that are and are not severely tested. In a nutshell, just keeping it simple, one basically tests several discrepancies from the test or null hypothesis and infers those that are well warranted and points to those that are poorly or terribly warranted. I've developed this long ago, but also with other people, with Arispanos, with Sir David Cox, and David Hand. So to avoid misinterpreting a two-standard error significant result, let's see, to put this very quickly, suppose we were interested in claims of the form mu is greater than some mu prime. We imagine we're testing mu less than 0 versus mu greater than 0. And our sample mean, let us say, is 2. Now, the probability that you would have gotten an X bar, a sample mean lower than 2, if it's only chance alone, is quite high. It's 0.98. And so the null had a good chance of surviving if true, so the severity is 0.98. As you move away, though, from 0 to severity assessments of mu greater than 1, etc., they get smaller and smaller, which is intuitively just right. What about fallacies of non-significant results? We know that failing to find a significant result isn't the same as having evidence of no discrepancy, but they're not uninformative, even for these simple significance tests. Minimally, learning that a test wasn't capable of distinguishing the effect from sampling variability is very informative. In some cases, so-called embedded cases, you can go further and also find an upper bound, an upper mu1, where you can say that there's good evidence that mu is less than that much. Okay, we have evidence it's greater than 0, but poor evidence that it's greater than 1, only 0.16, and a little better that mu is less than 2. And of course, it gets higher and higher. And again, this is logically sensible. Notice, okay, if you relate this curve, severity curve, to the second, this latter one, the second one, is paralleling power. So notice that severity goes in the opposite direction of power. And yet, you will sometimes hear accounts say that a result that's just significant at level alpha is actually stronger evidence that mu is greater than mu1 as the power against mu1 increases. How to explain that? One is, on a comparative analysis, you can view the data as asserting that the test rejects the null just at level alpha, say 0.02 as in our example. Then the numerator of this comparison would be the power. And so as it increases, we get more and more evidence. But this makes no sense. It's tantamount to saying something like, we have better evidence that mu is greater than 10 than that mu is greater than 2. So that's the problem with mixing and matching pieces from different accounts. Now for a quick recap, we hope to stitch them together into a what's happened so far. We began with the skeptical consumer who asks, show me what you've done to rule out ways you can be wrong. Biasing selection effects alter a method's error probing capacities, and these endanger all methods, but many of them lack the antenna to pick up on them. Fisherian and Neyman-Pearson tests can block threats to error control, but pathological battles result in their being viewed as an inconsistent hybrid where Fisherians can't use power and Neyman-Pearson can't report attained p-values, which makes them forfeit features that they each need. We say that you can keep the best from both Fisher and Neyman-Pearson, but use error probabilities inferentially. What alters error probabilities alters well-testedness of the claim post-data. Rivals to error statistical accounts condition on the data. The evidence comes through the likelihood ratio, and the result is error probabilities drop out. To the likelihood principle holder, what could have happened but didn't is to consider imaginary data, but to the severe tester, probabilists are robbed from a main way to block spurious results. The two groups really talk past each other. Bayesians may block inferences based on biasing selection effects without appealing to error probabilities by giving a high prior belief to the null hypothesis of no effect. And then you can get a high posterior probability to that null. But there are several casualties. One thing, it puts the blame in the wrong place. It's not clear how to obtain and interpret them. And there's just increased flexibility. Recent views among statistical thought leaders lead some to recommend abandoning statistical significance and p-value threshold. The casualties there, well, it's a bad argument that we shouldn't use a valuable method because it may be used badly. Or letting the tail wag the dog. No thresholds, then it's no test, and then no falsification. So it's much harder to hold researchers accountable for biasing selection effects. And of course, if you don't have tests, you don't have tests of assumptions. We recommend reformulating tests to report the extent of discrepancies that are or are not indicated with severity, and we can avoid fallacies this way. Now, confidence intervals, which I didn't get to discuss, would also be automatically reinterpreted. Instead of a single confidence level, we would look at several levels corresponding to different severity values for the points within the interval. So you need to ask, in appraising statistical reforms, what's their notion of probability? And secondly, what's their account of statistical evidence? Do they accept or not the likelihood principle? Of course, if the parameter has genuine frequentist distribution, frequentists can use them too, which makes the whole thing deductive updating rather than inductive inference. There's a silver lining to distinguishing rival concepts. You can use different methods for different contexts, and maybe we can stop refighting the statistics wars by 2034. By contrast, some people say we should reconcile tools with different aims, but the result there is to lead to increased conceptual confusion. In the context of skeptical consumers of statistics, then, there are 4 things required. First, that the method be directly altered by biasing selection effects, that you be able to falsify claims statistically, that you be able to test the model assumptions and block inferences that violate the minimal requirement for severity. So when you're in this context, absolutely, you should not throw out the error control baby with the bad statistics bathwater. Thank you very much. I look forward to the discussion.